Hi, scholars. We are going to start chapter 2 on quadratic functions. So in chapter 1, we did parent functions. Now we're specifically going to zero in on just quadratics. They're also called parabolas, conic sections, x squareds, all kinds of stuff like that. So the vocabulary we're going to talk about is quadratic function, parabola, vertex of a parabola, and vertex form. The objectives for 2.1 are to describe the transformations and to write the transformations. So you can just think of this as an extension of chapter 1. So describing them, a quadratic function is a function that can be written in the form f of x, so function of x, is equal to a times the quantity x minus h squared plus k, where a is not equal to 0. If a can be any other number. The U-shaped graph of a quadratic function is called a parabola. In section 1.1, we graphed quadratic functions using tables, but you can also graph quadratic functions by applying transformations to the graph of the parent function f of x equals x squared. So here's the core concept. We've talked about the same transformations in chapter 1. If you want to do a horizontal translation along the x-axis, the h here will move it along with the x. The original equation is x minus h, so if h is positive, it goes to the right. If h is negative, it goes to the left. Vertically speaking, the number out here we call k, and it moves it up or down. If k is positive, it goes up. If k is negative, it goes down. This is a description of how, if I have f of x equals x squared.
Describe the transformation of f of x equals x squared represented by g of x equals quantity x plus 4 squared minus 1. Then graph each function. Solution. Notice that the function is of the form g of x equals quantity x minus h squared plus k. Rewrite the function to identify constants h and k. Rewrite as g of x equals quantity x minus negative 4 squared plus negative 1. So h is negative 4 and k is negative 1. Because h equals negative 4 and k equals negative 1, the graph of g is a translation 4 units left and 1 unit down of the graph of f. Graph the parent function f of x equals x squared, then use this transformation to graph g of x equals quantity x plus 4 squared minus 1.
It's just the same we did in chapter 1. We're going to move on. Those are extra examples. So we also have reflections in the x. Remember, the reflections in the x changes your x's, your y's from positive to negative. If it's a reflection in the y, it only changes the x's from positive to negative. And this is symmetric. So y equals x squared is its own reflection in the y-axis. We also did horizontal and vertical stretches. Remember, they look the same, but their movement is different. So a horizontal stretch goes sideways. It goes away from the x-axis if a is fractional, and it shrinks toward the x-axis if a is greater than 1. And that's if the number is in the parentheses with the x. If the a is just outside of it and it's greater than 1, it stretches it, and so it gets skinny. If a is fractional and it's right next to the a squared, it gets wider because it makes it like squished. So here's another example.
Describe the transformation f of x equals x squared represented by g. Then graph each function. A. G of x equals negative 1/2 x squared. B. G of x equals quantity 2x squared plus 1. Solution. A. Notice that the function is of form g of x equals negative ax squared, where a equals 1/2. So the graph of G is a reflection in the x-axis and a vertical shrink by a factor of 1/2 of the graph of f. Graph the parent function f of x equals x squared. Then use this transformation to graph g of x equals -1/2 x squared. B. Notice that the function is of the form g of x equals quantity ax squared plus k, where a equals 2 and k equals 1. So the graph of g is a horizontal shrink by a factor of 1/2, followed by a translation 1 unit up of the graph of f. Graph the parent function f of x equals x squared. Then use this transformation to graph g of x equals quantity 2x squared plus 1.
More examples. Now we're going to talk about how to write the equation. And this is magic, so pay attention here. The lowest point on a parabola that opens up, or the highest point on a parabola that opens down, is the vertex. The vertex form of a quadratic function is f of x, function of x, equals a times x minus h quantity squared plus k. A cannot be 0, but the vertex, that actual middle point, is hk, as in these hk's right here. So A will tell you if it's reflected in the x or if it's a vertical stretch or shrink. H will tell you which way it goes horizontally. K will tell you which way it goes vertically. So you want to pay attention to these numbers. Here's another example.
Let the graph of G be a vertical stretch by a factor of 2 and a reflection in the x-axis, followed by a translation 3 units down of the graph of f of x equals x squared. Write a rule for G and identify the vertex. Solution. Method 1. Identify how the transformations affect the constants in vertex form. A reflection in x-axis and a vertical stretch by 2 indicate that the constant a is equal to -2. A translation 3 units down indicates that the constant k is equal to -3. Write the transformed function. First write the vertex form of a quadratic function. G of x equals a times the quantity x minus h squared plus k. Substitute -2 for a, 0 for h, and -3 for k to get -2 times the quantity x minus 0 squared plus -3. Simplified to get -2x squared minus 3. The transformed function is g of x equals -2x squared minus 3, and the vertex is 0, -3.
Just pointing this out, the 0 is the blue number.
Method 2. Begin with the parent function and apply the transformations one at a time in the stated order. First write a function h that represents the reflection and vertical stretch of f. Multiply the output, or f of x, by -2. Write h of x equals -2 times f of x. Substitute x squared for f of x to get -2x squared. Then write a function g that represents the translation of h. Subtract 3 from the output, or h of x. Write g of x equals h of x minus 3. Substitute -2x squared for h of x to get -2x squared minus 3. The transformed function is g of x equals -2x squared minus 3. The vertex is 0, -3. You can check your answer by using the calculator to graph f of x and g of x in the same viewing window. You can see that g of x shows the correct transformations of f of x and has a vertex at point 0, -3.
That shows you both methods. So here's another example.
Let the graph of G be a translation 3 units right and 2 units up, followed by a reflection in the y-axis of the graph of f of x equals x squared minus 5x. Write a rule for g. Solution. Step 1. First write a function h that represents the vertical and horizontal translation of f. Subtract 3 from the input, add 2 to the output. Write h of x equals f of quantity x minus 3 plus 2. Replace x with x minus 3 in f of x to get quantity x minus 3 squared minus 5 times the quantity x minus 3 plus 2. Remember that in order to multiply two binomials, you can use the FOIL method. For example, binomial x plus 1 times binomial x plus 2 is equal to x squared plus 2x plus x plus 2, which respectively are the products of first, outer, inner, and last terms. Returning to step 1, simplify to get x squared minus 11x plus 26. Step 2. Then write a function g that represents the reflection of h. Multiply the input by negative 1 to get g of x equals h of negative x. Replace x with negative x in h of x to get quantity negative x squared minus 11 times negative x plus 26. Simplify to get x squared plus 11x plus 26. So g of x equals x squared plus 11x plus 26.
Watch that as many times as you need to. Here's another example.
The height h in feet of water spraying from a fire hose can be modeled by h of x equals negative 300 x squared plus x plus 25, where x is the horizontal distance in feet from the fire truck. The crew raises the ladder so that the water hits the ground 10 feet farther from the fire truck. Write a function that models the new path of the water. Solution. Step 1. Understand the problem. You're given a function that represents the path of water spraying from a fire hose. You're asked to write a function that represents the path of the water after the crew raises the ladder. Step 2. Make a plan. Analyze the graph of the function to determine the translation of the ladder that causes water to travel 10 feet farther. Then write the function. Step 3. Solve the problem. Use a graphing calculator to graph the original function. Because h of 50 equals 0, the water originally hits the ground 50 feet from the fire truck. The range of the function in this context does not include negative values. However, by observing that h of 60 equals negative 23, you can determine that a translation of 23 units in feet up causes the water to travel 10 feet farther from the fire truck. So, add 23 to the output or h of x. Write g of x equals h of x plus 23. Substitute for h of x and simplify to get a negative 300 x squared plus x plus 48. So the new path of water can be modeled by g of x equals negative 300 x squared plus x plus 48. Step 4. Look back. To check that your solution is correct, verify that g of 60 equals 0. G of 60 equals negative 300 times 60 squared plus 60 plus 48, which equals negative 108 plus 60 plus 48, which is equal to 0. So g of x does model the new path of the water.
And that's the end of our section.